So we'll continue to study physics by talking about the concept of work and how it relates to energy. In physics, work has a very specific definition. It's the transfer of energy. So we're going to let energy move around. We're going to actually use energy to do something by applying a force. This is the force that we've already studied. We're used to studying forces. And we're going to apply a force to make an object be displaced. So we apply force to get a displacement. That's how we define work. Of course, in physics, we like to define things with equations. The equation that we're going to use for work is equal to a force, F, multiplied by a displacement, and then we have to multiply by the cosine of the angle separating those two. So F is the force, D is displacement, how far you travel from where you start, and theta is an angle between F and D, between the force and the displacement. So if I have, let's say, a force that's acting up, so we can draw that as a vector. I have a displacement that's acting entirely to the right. That's also a vector. The angle between those two is going to be equal to 90. So this force actually isn't applying at all in the same direction as my displacement. So this force is not responsible for any of this displacement. They're operating completely perpendicular to each other. So in this case, if I take the cosine of 90, I get 0. So this force actually does no work. So when your force and displacement are perpendicular, you get no actual work out of that. If the force and displacement are both parallel to each other, they're acting the same direction, then your angle is going to be equal to 0, and the cosine of that angle, cosine of 0, is going to be equal to 1. So in that case, your work is going to be its maximum value, and work is going to be positive. You can also have situations where your force is acting one way, maybe backwards, but your displacement results in going the complete opposite direction. So this would be anti-parallel, or theta. The angle between these two is 180 degrees. So if that's the case, then the cosine of 180 degrees is equal to -1. And in this case, your work done by this force is going to be a negative value. So those are 3 good examples of forces being applied to do work and how work actually is defined. And to really understand work very well, we need to understand how it's related to energy. And we'll start by talking about the concept of kinetic energy. Kinetic energy has a very easy definition. It's energy in motion. Energy related to actually moving. Any object that's in motion has some kinetic energy, and we can define this in physics as kinetic energy K is equal to 1/2 of whatever the object's mass is times whatever its velocity is squared. So that's going to be your kinetic energy, and it's related to work through something called the work energy theorem, where the net work is equal to 1/2 your mass times your final velocity squared minus 1/2 your mass times your initial velocity squared. So when you're doing applying energy to accomplish a task, the work that you do is equal to the change in your kinetic energy. So net work is equal to change in K. And this equation right here is what we call the work energy theorem. It is a fundamental result that you should learn in any kind of introductory physics class. But there's not just kinetic energy, we have other kinds of energy as well. We also have other kinds of energy, something like potential energy. And one of the main types of potential energy we want to be familiar with is potential energy due to gravity. So when you use work to do some kind of a function against gravity, then the work that you've done, the energy that you've put into doing that work against gravity becomes then potential energy that gravity can then do. The equation for potential energy, change in potential energy, is equal to m times g times h. And we can recognize this in terms of the equation for work, which was a force times a change in position. So m times g is just the force of gravity, and h is whatever height you've been lifted to. So that's basically just your change in position. So the potential energy equation is really just a statement, a restatement of what work is. And what we notice is that as an object falls, as gravity does work on an object, that potential energy, it actually changes form. Your height is going to decrease as you're falling. So if I'm on the top of a building, if I'm way up top and I start falling down, my h is gradually decreasing. So that means my potential energy decreases. But as the potential energy decreases, I'm speeding up, I'm going faster and faster. So my kinetic energy is actually going to increase. And what we notice when we drop objects is that whatever change in kinetic energy I have, whatever increase I have in kinetic energy is equal and opposite to the change in potential energy due to gravity. So as long as I ignore friction, ignore air resistance, any potential energy that I have due to gravity gets turned into energy due to motion, gets turned into kinetic energy due to my actual motion. So this will bring us to a very important concept that we know about energy involving its conservation. Before we talk about conservation of energy, we need to kind of understand some concepts behind forces and what kinds of forces actually do work. So we have a concept of conservative forces, and we've worked a lot with these already. This is when work that you're doing depends only on endpoints. So you don't care about what happens in between. We don't care about what path you take to get to your final point where you're doing your work. We only care about what happens at the beginning versus what happened at the end. Nothing in between matters. There's another kind of conservative force that we haven't talked about yet, something called a spring force. This is a good example of a conservative force. So a conservative force is one where the endpoints are the only thing that matters. An additional consideration for conservative force is the energy that you can get out of a spring. So potential energy due to a spring, we can quantify this as an equation, 1/2 kx squared. Potential energy due to a spring is a conservative force. It depends on k, which is something called the spring constant. And the spring constant physically tells you how stiff your spring is. So the spring constant is the stiffness of a spring. If you have a stiffer spring, you have more potential energy contained within that spring. It can do more work. It can push on things more. And then x is the displacement of your spring. So in order to make a spring actually move, to make it actually do something, you actually have to move the spring. And this x tells you the displacement, either how far you stretch it, or it can be how far you compress your spring. So we have potential energy due to a spring in terms of conservative force. And when we only have conservative forces acting, we are conserving something called mechanical energy. The energy in your system is conserved when you're using conservative forces. Mechanical energy conservation. And in the case of conservative forces, you have maybe some kinetic energy at the beginning, we'll call it kinetic energy initial, plus some potential energy at the beginning, potential energy initial, and that has to be equal to whatever final kinetic energy you have, plus whatever final potential energy you have. And we can now remember the potential energies that we could have. We could have potential energy due to gravity, or we could have potential energy due to a spring. So far, these are the two types of potential energies that we know about. Potential energy due to gravity or potential energy due to a spring. and before is conserved with whatever happens afterwards. And in addition to conservative forces, we also have non-conservative forces. So non-conservative forces do care about the pathway that you take when you're using your force to apply some energy to move something, some displacement. So these are path dependent. The primary non-conservative force that we've talked about so far has been friction. So you can think about this. This should make a bit of sense. As you push something along a floor, you're doing more energy, you're expelling more work the farther you push it. So you try to kind of find the shortest path because friction is increasing the amount of work that you have to do, the amount of force that you have to overcome. And it's path dependent. So it cares about your initial and final positions. This conservation of energy actually works with conservative or non-conservative forces. We conserve energy no matter what. You might have heard about this in other courses in kinds of chemistry or in kinds of thermodynamics. This is kind of basically the first law of thermodynamics. Energy isn't created or destroyed, it stays the same. So the energy that you have initially is equal to the energy you have finally. Before you do something and after you do something, the energy remains the same. So you could have kinetic energy initial plus some potential energy initial, PE initial, that's comprised possibly of potential energy due to gravity initial plus potential energy due to a spring initially. And then we can add on work due to non-conservative forces. So if you have non-conservative forces going on, things like friction, then that's going to change your kind of energy balance. And the final energy that you're going to get out is going to have to be equal to final kinetic energy, K final, plus the potential energy final, which again can be due to gravity or can be due to springs as far as we're concerned so far, plus maybe some other energies that are out there. Final. Maybe we have some other energies initial that we would need to consider, so we can add some other energies initial. Some examples of these other energies that we might get. We might have some chemical energy, maybe from a battery. We might have electrical energy. We might have radiant energy. We might have nuclear energy. We might have thermal energy, all sorts of different types of energy that we can include in here just to make your energy balance out so that the energy you have in the beginning, energy initial, has to be equal to the final energy. And you balance these two equations so that they're the same. Something important to understand is really the purpose of doing all this work and this conservation of energy. Why do we even care? Well, we want to use energy to accomplish work, to help us do a task, to help us complete something. Maybe to move a big object, maybe to move information. We want to use energy to accomplish a purpose, to actually do something. And something we have to keep in mind is that in the real world, we cannot actually convert all of the energy that we use into useful work. There's always going to be some loss to the outer environment. And a lot of times these losses are in terms of these non-conservative forces. Something like friction. So if I'm running my engine and I'm turning kind of energy into heat to kind of turn my motor, I'm losing some energy in terms of thermal energy, in terms of friction, in terms of the energy of the motor actually heating up. So that's energy that I can't use to actually turn a piston. This is a fundamental result of physics, fundamental result of science. It's called the second law of thermodynamics. No matter what, you're always going to lose some energy in your system to something like heat or some other non-conservative forces. This doesn't mean energy isn't conserved. When I say we're losing energy, I'm not actually losing it. It just means that it's turning into something that I can't use to actually do something useful. The second law of thermodynamics has another name. You can look it up on Google. It's sometimes called entropy. If we actually want to apply how much energy we're actually getting out of something, we can quantify how good some kind of object is working, some kind of a piece of machinery, with something called the efficiency. E sub F, and we call this efficiency, is equal to the amount of work that you get out, so how much actual useful energy you're getting out, divided by the amount of energy that you're putting in. So work out, or energy out, divided by the energy that you put in. This ratio will tell you how efficient your system is. Then one final quick side note, very quickly. This is covered quite well in the textbook, but just to take note so that you have this equation. A lot of times when we're using this practically, we don't talk about work, we talk a lot about power. Power is just when you take your work and divide it by the amount of time that you're applying the work for. So the units of power are commonly seen all around you. They're called watts. This is a light bulb. That measurement on the light bulb is telling you how many joules of energy you're getting out divided by the seconds that it's outputting those joules. Joules per second is the unit of power.